I have started recording here. All right. So in lecture 12, we are going to design our own counter. And I want you guys to, sort of be the participants in this, counter that we come up with. So what we are going to do is we're going to take a simple example of designing a 3-bit counter, only 3-bit counter. So essentially that means that I can do anything between 0 and 7, right? So it's just going to be 3 bits for the counter. But I'm going to come up with my own choice, and essentially it's going to be your choice of how the counter counts. So it's going to be totally arbitrary, and I need your help in coming up with that arbitrary sequence, right? And we can take turns. Oh no, Bennett, we can't do that. No. All right, we are going to do it in a different way. We're going to do it in a different way. Now, in terms of certain limitations for this design, let us say we are going to use a JK flip-flop for generating the most significant bit of the counter. We will use a T flip-flop to generate the next most significant bit of the counter. And then we will use a D flip-flop to generate the least significant bit of the counter. Now, because all of you, 40 of you, are going to be participating in this exercise, I want to come up with some rules of how do you determine the counter sequence. The rules are: 1, the counter output can only be between the digits 0 and 7. That is simply because we have a 3-bit counter, right? So 0 to 7. I do not want any repetition of the digits. So I cannot do 0, 1 and then back to 1, right? So no repetition of digits is allowed. And I want you guys to skip 2 digits in this example. So if you have 0 to 7, that's 8 different values. I only want you guys to come up with 6. I want you guys to kind of skip over 2 values, right? So each student can take a turn and tell me the number it starts from. I need 6 values, right? So you guys can take turns, but only do one number per student. Don't do all the. Okay, so you got 6 from Colin, 2 from Bennett, 5 from Andrew. I need 3 more, guys. And now it's okay. So Andrew, 7 from Om. We did 3 from Colin, this time Melville, and then 4 from Dan, and that's it. Okay, so that's our counter. No, we are done. We are skipping 2 states, 0 and 1. We are skipping because I also want to show you how that works, right? So this is our arbitrary counting sequence. Our counter should go from 6 to 2 to 5 to 7 to 3 to 4 back to 6. Right? That's what we want it to do, while using a JK flip-flop, a T flip-flop, and a D flip-flop. Everybody okay with this so far? What we are trying to do, our counting sequence is sort of all over the place, right? It's skipping some states. It is jumping up and down. There's no pattern here. So, isn't this a question on the exam? Maybe very, very likely to be on the final exam, but I usually do this on the second exam or quiz 3. Sure, yeah. It's a very time consuming yet simple exercise. Let's go through it. Step 1 is going to be to draw the state transition diagram. Now, a state transition diagram includes states and transitions, right? Of course. Multiplexer multiplexes, decoder decodes, encoder encodes. A state transition diagram has states and transitions. in a diagram form. So we are going to attempt, the first step is going to be to draw this state diagram or state transition diagram. So what I'm going to do is I'm going to go back and take a look at my sequence that I need to generate. This is 625734, right? So I'm going to copy this over here, 625734. And then it goes back. Now, if I wanted to draw the state transition diagram here, I'm going to draw circles representing states. How many states do I have? I have 6 unique states in this problem. So I'm going to draw 6 circles. I think I can go ahead. One. No, I don't want it to be shaded inside. So I've got 6 circles over here. And I can use some arbitrary names for the states. So I can call this say S0, S1, S2, S3, state 4, state 5. I've got 6 different states over here in which the counter output is going to be 6. Let me use a different color. 6 to 2 to 5 to 7 to 3 to 4 and back to 6. Those are the things that you guys came up with. Now, how is it going to go from one to the other? Well, from 6, it will go to 2. From 2, it should go to 5. From 5, it should go to 7. From 7, it should go to 3. And from 3, it should go to 4. And from 4, it should go back to 6. Right. So this is sort of our problem here. What are the states indicating? States are the value of the counter, right? So let me write that statement here. States are value of counter. And transitions are essentially indicating the state transitions, right? Indicating state transitions. Now let me sort of zoom in to this to talk more about what this state 0 is, right? So when I say state 0 is 6, what I really mean is there are 3 flip-flops in my design, and the decimal value of the 3 outputs should be 6, right? So if I have, say, for example, if I have QA, QB, and QC as the 3 outputs of the 3 flip-flops I need to do this, it should be 0, 1, and 1. That's 6 essentially. And then whenever I have an active edge on the clock, you see this transition happens when the transitions happen when there is an active edge. It could be positive, could be negative. Active edge on clock. So from 6, it should go to 2, right? So what does that mean to okay. That means QC plus, QB plus, QA plus, right? The next states should be 0, 1, 0. You guys see that? And that same thing is applied all over the place, right? For this guy, it's going to be 1, 0, 1, and this guy is going to be 1, 1, 1, and then 0, 1, 1, and 1, 0, 0, right? So each flip-flop is responsible to generate one of these three bits, either QC or QB or QA. I'm just using QA as our least significant one, right? With the output of the D flip-flop in our case. That completes my state diagram. I'm going between state 0 to 1 to 2 to 3 to 4 to 5 and back to state 0. And my counter values are 6, 2, 5, 7, 3, and 4. All right. Questions about completing step number 1. So the first positive edge of the clock, first active edge of the clock goes here. Second active edge of the clock goes here. Third active edge, fourth active edge, fifth active edge, and sixth active edge, it comes back. Now let me ask you guys this. Where does this start? Where does it start? Does it start in state 0? Does it start in state 2? Where does it start? This is any of them. That's right. Any of them. Could be 0, 1, 2, 3, 4, 5, 6, 7, right? It could even start up in one of the states that we are actually skipping, right? So we have actually skipped a couple of states. Let me draw them here. Maybe here and here. We have not even included these guys. What is this? This is a 0 and a 1, right? Yeah, 0 and a 1. So 3 zeros and 0, 0, 1. We have not even included these guys. So it could start in one of these 8 states. Now the thing is, because I'm designing this guy, if it starts in, for example, 3, it will do 3 to 4 to 6 and then fall in place. Later on in the lecture, we will also try to figure out what happens if it starts in a skipped state. Does it come into our counter, or what happens then? Like, let's try to figure it out. All right. Second step in our counter design is to derive the state transition table. Because I have cues, right? Because I have outputs of the flip-flop going to the next state output of the flip-flop, then to the next state output of the flip-flop, I'm going to need to figure out what should I give at the inputs of those flip-flops such that these transitions happen. So I'm going to be needing the excitation tables of my JK, T, and D flip-flops in order to come up with those relationships. So let's try to draw the state transition table here. So what I'll do is I will draw a really big table here. I need here, and I need 3 more here, and then I need 2, 1, 1. Okay. So let's say we have QC to indicate the most significant bit of the counter, QB and QA, right? These are 3 outputs of the 3 flip-flops that we are going to need. Why 3 flip-flops? Because we have a 3-bit counter to design. And this is going to indicate our current state, current circle you are in. Next, this is going to transition to QC plus, QB plus, and QA plus. This is our next state. And then I need to figure out what I should give at JCKC. Why JCKC? Because I'm trying to use a JK flip-flop to generate the most significant bit of the counter. And for the next most significant bit, I think I used a toggle flip-flop, TB. And then for the least significant bit, I used a D flip-flop, DA, right? So I need to figure out all those using excitation tables. So that's going to be sort of the most time consuming step in our process. Well, one of them. Let's try to fill this out now. I can go 0, 1. Maybe I can go, sure, 0, 1, 0, 1, 0, 1, and 0. Yeah. Can you do this very nicely? I'm going to do this. All right, this should do it. 0, 1, 0, 1, 0, 1, 0, 1. 2 zeros, 2 ones, 2 zeros, 2 ones. The current state of the flip-flops can be any one of the 8 states of the flip-flops. That's the current state. And the homework asks us only to use T flip-flops. Yeah, that's it. Only T flip-flops for the homework. All right, so that's your current state. Now, to talk about the next state, we need to go back and take a look at what you guys did. So how about the first one? 0, 0, 0. Well, that is not even part of my counting sequence. So the designer doesn't even care what the next state is. It's not even part of my counter, right? Because you see this guy over here, right here, and 1. So for both those guys, I don't even care what the next state is. So I'm going to do XXX there, which also means that all these guys are X, don't cares. The same thing happens even for 1. Don't care because it's a skipped state. Don't care because I don't care what you give at the input, because I never will care about a current state being a 1 so far. Now for 2, what is the next state for 2? Because that's what we have here, right? 2. All right. So it looks like after 2, I should get 5. 5. All right. So let's do that. 5. I got 1, 0, 1. After 3, what do I have? I have 7 after 3. Yeah, I think I have 7 after 3, right? No. After 3 is 4. 3 after that is 4. So 3 transitions to 4. 4 transitions to what? 4 transitions to 6. 5 transitions to 3. 5 transitions to 7. 1, 1, 1. 6 transitions to, I believe, 2. 6 to 2, yes. And then 7 to what? 7 to 3. You guys okay with filling up the current state and the next state table? The first 6 columns are okay. Yeah? Yes. Now we are going to take a look at the excitation tables of these 3 flip-flops to fill out all the others. So let's take a look. In order for me to come up with JC column, I need to look at QC and QC plus. You guys see that? All right. So the first 2, sure, they don't care. The next one is what? 0 should transition to a 1. If 0 transitions to a 1, what should I give over here? I need something to save time. What should I use to save time? All right, I will use this to save. This one, I think it will have somewhere that state transition table. All right, I have it here. So what I'll do is I will simply take a snapshot of this guy. Come back to our lecture here and then paste it somewhere here. All right, hopefully I can, at the end, maybe I can delete it. All right, so I'm going to refer to this table here, right? So what do I have? 0 to a 1. 0 to a 1 is 1x. Next, 0 to a 1 again, 1x. 1 to a 1. 1 to a 1 is x0. And then 1 to a 1 again, x0. 1 to a 0. 1 to a 0 is x1. And then 1 to a 0 again, x1. I hope you guys are following along with this and you guys are sort of checking my work, because it's very easy to kind of go wrong over here. All right. So please do that. Now I'm going to, I don't think I need this anymore, right? I don't need this anymore because T and D are very easy. So let's focus on T. For that, I need to move this guy here and I need to move this guy here. Yeah. In order to come up with TB, I need to look at how QB transitions to QB plus. All right. So let's see. For the third one, toggles. For the fourth one, toggles. For the fifth one, toggles. For the sixth one, toggles. Doesn't toggle and doesn't toggle. At any time, if you guys have questions about how I'm doing this, you guys got to bring it up. I'm moving to the D. How will QA transition to QA plus? Well, the DA should equal QA plus. It's not going to be any. So DA is QA plus, right? That's the characteristic equation of D flip flop. So whatever is in the QA plus column, I'm just going to copy it over to DA. So I have what? 1 0 0 1 0 1. I've just copied over whatever was there in the QA column. All right, and then I can erase. Oh my! Fill entire stroke. Done, done, and done. And just so that you guys can sort of see this, I'm going to highlight this guy and I'm going to say this is achieved because of this and this column. Should DA be 0 1 0 1 0 1? Should DA be no. So you see DA is QA plus. So whatever I have over here, I'm just putting it over here. QA plus, yes. All right, questions, you guys? Okay, what is coming up next? You guys know? The next step is going to be to derive equations for the flip-flop inputs. So I'm going to have to find JC, KC, TA, TB, DA. K-maps, that's right. But small ones. So I'm going to find logic expressions for these four guys in terms of QC, QB, QA. Kang's maps. Oh man, Karnoff is going to turn in his grave. So we need to choose the flip-flops to implement your counter. We already chose the flip-flops, right? We already said JK and T and D. So we already chose JK for MSB, T next MSB, and D for the least significant bit of the counter. We already did that. Our next step is going to be to derive the flip-flop inputs. So for that, all right, you guys are getting bored of this. So let me pick up pace here. How is writing in tiny font more interesting and than generating your own flip-flop? Your own counter. All right. So the first thing that I'm going to aim at is JC, right? So essentially my step is going to be use how many variable k-maps do I need? How many k-maps do I need? I need one for JC, KC, TB, and DA, right? So I need 4 variable k-maps. Use 4 3 variable k-maps to write JC, KC, TB, and DA in terms of QC, QB, and QA, right? All right. I needed that, so I brought that up from there, and then now I will start with the A maps. Let's do the first one first. When you need to snap, you need do I need to do it for JC? Do I need to do it for JC? JC is 1, right? Yeah, that's right. JC is 1, right? XX 1 1 XXXXX. So F1. Yeah, you're right. I don't even need to do it for JC. JC equals 1. Like I don't, that's the simplest form. KC is QB. Yes. All right. So let's do it. Right. So JC, you guys see it. JC is 1 because you have don't cares and ones over here. So if you fill it up in your K map, it'll be don't cares or 1, right? That means you can combine it to make it 1. So JC is 1. That's already sort of, we've already come up with that. Let's move that by the side. We don't need that anymore. Now let's do it for KC. For KC, it's going to be QC, QB, and QA. 0 0 0 1 1 0 1 1. Oh no, sorry, 1 1 and 1 0. And then KC is X X X X 0 0 1 1. And the simplest group is going to be what? This guy. And that will tell me that KC equals QB. That's right. Now next for copy and paste it. Let's do the next one, which is TB. TB is XX11 1100. All right. So what are we doing here? I think we are doing these guys and these guys, right? So for this one, TB equals let's see, QB complement or QC complement. Is that okay? QC NAND, yeah, QC NAND. All right, fine. Yeah, QC NAND QB also works. All right, so that's your TB. Next, we are going to have DA. So let's paste it and say, what is DA? XX10. XX10. 0101. All right, a little bit more interesting here. And all of this is you guys decided that this was going to happen. So it looks like it's going to be this and this. Yeah. So DA equals what? I have QC complement and QA complement, or QC and QA, which is sort of QA exclusive nor QC. You guys agree with that? While we are doing this, I hope you guys are checking my work. All right, so we got the equations, right? Now we come to the last step of this design, which is simply to build the circuit, build the counter. Right, so we have got an expression here for DA. We have got an expression here for TB, and we have got an expression here for KC, and we have got an expression here for JC. Right, we have got all the 4 3-variable K-maps. Some of them we didn't even have to do because it was trivial, just like for JC, sorry. So if I go back, and that's my last step, which is to build the design. So let's start talking about how do you build this design. Okay. The first thing is going to be, this is how I do it, right? So I first draw my 3 flip-flops in the same sequence as the most significant down to least significant, right? So that's just a personal preference. So this is going to be my first flip-flop here, and the second one here, and the third one here. And then I can start labeling them, right? So I can say, all right, this is going to be my J and K, and then trigger. This is T, this is D, trigger, trigger. And then I've got Q here, and then Q complement here. Q here, and Q complement here. And then I've got Q here, Q complement here, right? Question about the TB K-map. I thought we ignore the don't cares if we just group the 4 don't cares. Let's see, which one? This one. I thought we ignore the don't cares if it's just a group of 4 don't cares. But we don't have a group of 4 don't cares, right? So we have, so for these 2 ones, I'm making a group of 4. And for those 2 ones, I'm making a group of 4 with these 2. Oh, okay. Yeah, if they were don't cares, we would ignore it. All right, let's come back. All right, so we got J, T, and D, right? Now let's after you're done with that, let me also put in the clock. So let's say I have a clock here. And the same clock gets connected to here. It is a synchronous counter, right? What does a synchronous counter mean? Every flip-flop is switching from one state to the next at the same time. So this is an example of a synchronous counter. everything is synced up to the clock. And I have chosen it to be a positive edge triggered counter. You might as well, you might have gone with a negative edge. It's up to you. Connection. All right. And this is my clock. Right. Okay. So now I need to figure out what I need to connect at J. Okay. It looks like JC should be 1. Always connected to high. So I can pull it up using a pull-up resistor to say plus 5 volts. J is hardwired to 1. How about KC? KC is QB. All right, where do I get QB from? Is there a QB available to me? Right there. Output of the T. That's right. So the output of the T went into the input of this guy. Okay. So I'm done with JC, KC. I'm done with that. All right. How about next? KC, KC. TB is QC NAND QB. Or I could put an OR gate with this. Any which way will work, right? So let's say I use QB complement and QC complement, put them through a OR gate and go into TB. Where should I put it? So this is my QC. This is my QB. And this is my QA. And this is my QA complement, QB complement, QC complement. Right? Okay. So I need QB complement, QC complement, put them through a OR gate. Okay. Yeah, I don't know. If I use that guy and that guy, it's not going to be... I will just draw an OR gate. QB complement, QC complement. This goes into TB. That's your TB. Yeah, see that? So you're taking this and you're taking this and you're putting it to TB, which is you are connecting here. Yeah, this is not hard. Yeah, exactly. All right. So we have got that. We have figured out TB. Now we are left with only D. All right. What is D? Exclusive NOR between QA and QC. Can I do this over here? This and going into that. I don't know. I may just choose to do this. This one will be DA, and then this will be QA, and then this will be QC. Let's color code it. Maybe all of them green. This one will be QA. This one will be QC. And this one will be your DA. Can we put the gates down there as long as we label signals? Yeah, yes, Bennett, you can. My goal over here is not to draw them all sort of in a confusing manner. I want you guys to clearly see my circuit, which is why I'm doing it. So yes, absolutely. So what is the output of the count? I'm done with it, right? I think I'm done with it. Yeah, I'm done with it. So what is going to tell you the output of the counter? Well, let me draw the 3 signals that actually matter as the output of the counter. Which this is going to be, let me draw it in red. right? Those are the three: QC, QB, and QA. Those will tell me the value of the counter output. Yes, QB, QC, QB, QA in that order. Yes. All right. Questions, you guys? Now, I want you guys to look at it this way, right? We were able to design a 3-bit counter with an arbitrary sequence using a variety of flip-flops, right? So, it's very easy to come up with your own problems here, right? So you could come up with your own counting sequence and you can say, all right, I'm going to use T flip-flops. Let's do it. Then, some designs can be a little bit more complicated than others, but that's the same procedure that you would follow. All right, now we have left one question unanswered. So we have built this circuit here, right? And now suppose we turn it on. Now when you turn it on, the initial value of QC, QB, QA could be 0, 0, 0, or it could be 0, 0, 1. What happens if that is the case? If we need to discuss the random power-up states. So the question here is, what if the 3-bit counter randomly powers up in the value? We need to pick one or the other, either the 0 or the 1, right? What do you guys think? If it powers up at 0 or powers up at 1? Would you need to manually find out? Yeah, we need to manually find out. That's right. But I need to pick the random power-up state here. I've left a blank. So for a student who has not taken a turn, you can either pick a 0 or pick a 1. Jeremy says, Tom says 0, 0. All right. So I think Tom did not get a chance. So let's start with 0. Going against the grain. All right. So let's say if it powers up with the value of 0, what happens? And I suppose you can see you have already designed it. So you should be able to backtrack, reverse engineer, and find out what would happen if this is your implementation, right? So let's try to go and see what it is, right? Randomly powers up at 0. Okay. So the question is, I go back all the way to step 2. If you have 0, 0, 0, what are these is what you are trying to find out, right? What are these? That's exactly what you're trying to find out. Well, if you want to find out what are these, then you need to know what are these. How will we know that? Well, we have used K-maps. So if we grouped the don't care, we considered it as a 1. If we left it out, then we have considered it as a 0, right? So let's try to take a look at whether we have considered it as a 1 or a 0. For JC, I know that JC was 1, so we considered that don't care to be a 1 for JC, right? How about for KC? Did we consider it as a 1 or a 0? We left it out, right? We left it out of the group. Let me highlight it in a different color. Maybe brown. We left it out. So it was a 0 there. For JK, it was a 1. But for KC, we left that don't care out. Exactly what? Where am I looking at? I'm looking at QC is 0, QB is 0, QA is 0, right? That's the place I'm looking at. 0, 0, 0. What is it going to next? For KC, you had a don't care, but you didn't make it part of the group, which means you consider you have sort of made it a 0, right? That was a 0 there. All right, let me come back here and put a 0 there. Now if you know JC and KC, what are we doing here? J is a 1, K is a 0. So we are doing a kill operation, right? So if you do, we are doing a jump operation. If you do a jump, you have essentially made this a 1, right? Because of the way you have implemented your circuit. Now let's go for TB. Let me do this quickly here. If I go and take a look at TB for the same spot, it looks like I have included that in my group. So I'm considering it as a 1 over there. And even for D, it looks like this guy is a part of my group. So I'm considering that as a 1. So for both toggle and data flip-flop, I have used that particular don't care situation as part of my group. So I'm considering it to be a 1. If I go back, that means that I need to change this to a 1, change that to a 1. Which also means I can figure out what is QB plus and QA plus. 0, please toggle, you become a what? A 1. 0, the data input is 1, so QA also is 1. So now we have essentially evaluated what happens when you randomly power up in 0, 0, 0. You actually go to 7, which essentially means I can now draw this guy. Maybe better. You guys see that? So if you randomly power up in 0, you actually go to 7, then you are in that 3, 4, 6, 2, 5 cycle. You come into the loop. But this is not something that you can sort of predict, right? It is possible that if you start in a random power up state, you might never come inside the counting loop. That is also possible, right? So it totally depends on how you have implemented your counter right here, how you have built your counter. Totally depends on that. So you have got to backtrack it from the K-maps and your circuit that you have built. How do you stop the counter from getting caught in loops that are not intended? You have to force it. Would not happen here, but that is if we toggle 0 and 1. Yeah, that's right. So if it always remained outside the loop, then you have to go in and actually force that to, instead of allowing it to be a don't care, you have got to change it to something that you intend to do. They just wouldn't be don't cares. That's right. Because now you care. Now, you guys can maybe on your own try to figure out for the same counter, what happens if it randomly powers up in 1, right? You can try to figure it out by filling up this one. Does it, does it come into the loop? Where does it come into the loop? Or does it just go to 0 and then go to 7? You try to figure that out as an exercise. All right, questions here. How do you handle random power up states? So it looks like the counting sequence is 0, 7, and then you're back into the sequence, right? The 3, the 4, the 6, the 2, 5, and then it'll go to what? It'll go to 7 again. All right. Now, in the next few minutes that we have, I want to talk about a different type of counter, which is called a ripple counter, also called as the asynchronous counter. And the reason why it is called an asynchronous counter is because of how we are connecting the clock input. Notice over here, we have 3 toggle flip-flops, 1, 2, and 3. We have connected the toggle input of each of the flip-flop to a 1, right? So all the 3 toggle flip-flops are always going to be in the toggling state. Now, if you want to design counters, what you can do is you can take the output of the first counter and use that as a negative edge trigger for the next one, right? So QA is actually becoming the negative edge effectively as your clock for the next stage. QB is becoming the clock for the next stage, and so on. And if you do that, you notice what happens. This clock is going to keep on going, right? So QA will toggle every time you have a negative edge on the clock. So those two are sort of pairs, right? This guy and this guy. QA will toggle when you have a negative edge on the clock. That is essentially determining that toggles. So QA toggles based on the negative edge of the clock. But because you are connecting QA to the clock input of the next T flip-flop, we are essentially saying QB toggles. See this? QB toggles when you have a negative edge on QA. You see where that happens. This is the negative edge on QA. That's when B toggles. The next negative edge on QA is right here. That's when B toggles. The next negative edge on A is here. That's when B toggles. See that? That is called a ripple counting behavior. That's an alternative to the synchronous design that we did. Now, again, if you continue this, you can say QC will toggle every time there is a negative edge on QB, right? There is a negative edge on QB over here. QC toggles. There's a negative edge on, that's it. That's the only negative edge on QB. How is this how the 74x counters are designed? No, so this is ripple counters. Those are not ripple counters. Those are synchronous counters in 74x, because it's all connected to that same the same clock input is being used to trigger all the flip-flops in that chip. This has some serious problems, which I'm going to talk about. This looks very simple, right? Just connect all the toggle inputs to 1 so that all the flip-flops are always toggling, and then use the output to trigger the next one. Use the output to use as the clock input, right? So this will work, but the problem with this is because there is going to be a propagation delay, you are going to have unintentional counter values. So for example, if you look at what happens, if you look at the behavior of the 3 outputs, QC, QB, and QA, every time you get a negative edge on the clock, QA changes. Every time there is a negative edge on QA, QB changes, but there is a propagation delay through that. And every time QB has a negative edge, QC changes, right? And there is a propagation delay because of that. Now, if you go back and take a look here, what are we counting? We are counting 0, 1, 2, 3, and so on, right? So if you look at QA is your least significant. So this guy is a 1. This guy is also a 1. And this guy is a 0, right? So at that time, we are in sort of the 0, 1, 1 state. Like that's 3. Our next value that we intend is a 4, right? The counter should increment by 1, should go to 4. Does it? Look at this. Over here, you have a 1 there, you have a 0 there, you have a 0 there. So eventually, you get a 4. But in the middle, you get a lot of transition counts that you don't want ideally. What are the transition counts here? Well, 3 will soon become 0, 1, and 0, which is a 2. Then you go to 0, 0, 0, which is a 0. And then you go to 4, right? So you're actually not going from 3 to 4 directly. You're actually going from 3 to 2 to 0 to 4. And these two guys are called, in this case, transition counts. Counts that are a result of propagation delay through the flip-flops. We didn't have to deal with this in the synchronous design because everything was in sync with one master clock. But we have to deal with transition counts in the ripple counter behavior. Now, here is where I want to leave you guys with. You have put all these guys to a high and you have connected the outputs into the negative edge of the counter. And if you connect the true outputs to the negative edge, you get a counter that goes from 0 all the way to 7. Can you make very few changes in this? This is what we call a ripple up counter, right? So this is a 3-bit ripple up counter. Why is it rippling? Because the effect of the clock ripples through the 3 flip-flops. What if you wanted to design? What would you change in this if you wanted to design a ripple 3-bit down counter? What if I wanted it to go from 7 to 0? What would you change? The answer is quite simple, but I want you guys to kind of play with it a little bit. To see what would you change in this to convert this up counter to this is counting up, right? 0 to 7. What would you change to get a ripple 3-bit ripple down counter? QN to clock. That's right. Yes. So you guys can sort of play with it, see if yeah. So you guys are almost there. Try to make the connections and then try to see if you actually are able to do that. But the change is very subtle, very simple change, and you will be able to design a ripple down counter. And I want to leave you guys with that exercise to kind of explore. I will share the answer when we come back in the next class, but I want you guys to play with that a little bit. All right. So the problem with ripple counters, very simple, right? All toggle flip-flops are connected to sort of a 1, and then the clock kind of ripples through. The problem is the transition counts, right? So if you were sensitive to the output count, the counter, what the counter outputs, you actually wanted for it to go from 3 to 4, and your design application could never deal with the transition counts, then this becomes a bad option for you. All right, I'm going to stop recording here.